How you guys doing? Still cool? It's all good still?
Great.
No exhaustion? Ah.
For me, it's usually about halfway through week 3 that I'm sort of like, wow.
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 I don't know. I mean, I would be dead after the first 2 days. But. Huh? Well, if I was, yeah, but I'm not listening to all the lectures. No, I'm kidding. No, I am listening. No, but if I was, yeah. That was a wise-ass comment. I'm ready.
All right, let's get started for the afternoon session. Back with Nima, talking about effective field theories.
Alrighty do. So, last time we got to the point in our discussion of the Wilsonian picture of the normalization group and effective field theory of making a couple of sort of technical statements that that we then spent some time talking about. But these were the statements that whatever your effective Lagrangian is, whatever higher dimension operators or relevant operators it might have, that in a precise sense, despite the fact that it appears the theory has infinitely many parameters, and et cetera, the fact that the parameters are suppressed by some mass scale already intuitively suggests that when you go to very low energies compared to that mass scale, most of them shouldn't matter. And despite the effect of quantum mechanical quantum corrections, loop corrections, that statement ends up being true. The naive statement would have been that you can simply drop all the irrelevant operators, and the correct statement is that you can't simply drop them if you have a fixed model. You can drop them at the expense of changing what you meant by the marginal and by the dimensionless and the relevant operators. Again, up to corrections of order p squared over the cutoff squared. Okay, so that was the first statement, which is the sort of which is the summary of the fact that we don't need to know the theory of everything in order to be able to do physics at low energies, right? So whatever's going on at very high energies gets absorbed into a effectively finite number of parameters. And the second statement, which is more closely related to the classic statements about renormalizability, which, as I emphasized at the end of last time, there's no fundamental distinction between renormalizable and non-renormalizable theories. It's just a matter of how accurately you want to model physics. If you want to model physics to accuracy that has some powers of the low energy squared divided by the cutoff squared, you've got to keep more and more irrelevant terms. Okay, but in any case, if we've decided that we don't care about the power suppressed things and we only care about everything else, then having set the irrelevant couplings to 0, it's further possible to change the relevant couplings, marginal relevant couplings, with the cutoff in such a way that the physics is fixed. And the way in which that's done is encoded by this Wilsonian renormalization group equation. And as we emphasize, this statement has real teeth because graphically it implies certain, not 100% obvious relationships between computations that you do at 100 loop order being determined by things that you do at low loop order, right? So all the leading logarithms are determined by 1 loop calculations, all the subleading ultraviolet logarithms are determined by 2 loop calculation, and so on. And already from our discussion, it's clear that the fact that that's true tells you that the way to organize your thinking about perturbation theory is not graph by graph, but scale by scale. So these logarithms, as we said 100 times, are things that get equal contributions from all scales. That's why it's kind of a misnomer to call them ultraviolet divergences. They're really things that are sort of get equal contributions from everywhere, from every scale, from low to high. And therefore, the correct way to organize your thinking about perturbation theory is to go gradually. Okay? Is to think about the physics scale by scale. All right, and so we interpreted the sort of the physical consequence of these statements. So now it's time to prove them. All right, so I'm going to give a sketch of the proof. This is essentially the sketch that you'll find in Pulchinsky's TASI lectures, and that you'll also find in Pulchinsky's 1984 paper on this subject. And I assure you that with all the details, there's nothing important that's missing relative to the sketch. Okay, so we could just spend a long time with a lot of indices and a lot of extra irrelevant complication to obscure the basic, extremely simple idea. Once you get this very simple idea, if you have like a spare moment or two some Sunday evening, you can sit down and look at the actual paper and dot all the I's and cross the T's. But there's nothing missing after the basic points that we'll cover today. All right. So let me remind you what we're trying to do. We're trying to do this path, and we're trying to compute the Green's function at low momenta relative to the cutoff. So express everything else. So this is this path integral with some phi p1 through phi pn e to the minus s of phi and the cutoff. But since all the momenta here are small in the cutoff, and in particular all these momenta are way small in the cutoff, we can rewrite this as an integral where all the p's are less than lambda prime of phi p1 through phi pn of e to the minus some nu s of phi and lambda prime, where of course that nu s is just the path integral over all the modes that were stuck between the old and the new cutoff, e to the minus s of phi and lambda. All right? So, now, what we'd like to do is not do this integral in one shot, but write down a differential equation for how this effective action varies with the cutoff. Okay, and it's possible to do that. This is known as the exact Wilsonian normalization group equation, or sometimes the Wilson-Pulchinsky equation. Okay? So there's a Wilson-Pulchinsky equation. Tells you that there's a formula, lambda dd lambda, s of phi lambda is some functional of s, which we're going to determine in a moment. Okay, and this is exact. Now, if any of you have heard of this, you might be excited that you can say something exact in quantum field theory. After all, many things in this school are about exact results in field theory that involve a humongous amount of fancy, schmancy, hard, and interesting and fascinating work. And we're going to, in a moment, in 30 seconds, write down an exact equation. All right. Now, there's a moral in this. Cheap exact equations are useless. This is a cheap exact equation, and it's actually practically useless. Okay, and we'll see how it's practically useless. For example, you might say we have an exact normalization group equation. What the hell are all these losers doing calculating 3-loop beta functions in QCD? Nah, they can just do this exact thing and get the answer. No, they're not losers. Okay, and you're going to see the point here that this useless RG is not a practical RG. It's not the RG. For example, for phi to the 4th theory, this is not the RG that tells you lambda dd lambda of the couple that the scale variation coupling is 3 lambda squared over 16 pi squared. The formula that we know and love from last time and you've all seen, we do not get that from this exact RG equation. Okay, so this is an exact and pretty useless equation. What's very important about it is the conceptual point that such an equation exists. That's all we need to know. And this is really encoding that we've decided to think about physics scale by scale rather than order by order in the loop expansion. In general, there are a number of sort of deep and useless equations in physics, like the Wheeler-DeWitt equation is another one, right? So in general, you should be suspicious of deep, useless equations, right? They have some use, but anything that comes too cheap is probably not quite as profound as it seems at first. Here, there is something profound going on, but it's not the fact that there's an exact equation. It's the fact that we should be thinking about the physics scale by scale. All right, now, let's get an idea of what this equation looks like. So the kind of crucial thing here is that we're looking for a differential equation. So in other words, what we're integrating out are just the modes in a thin shell, right? We want to go from lambda to lambda prime and integrate out everything in this shell of momenta. But we're going to do it gradually. So we're going to do it from lambda to lambda minus delta lambda. Right? So we're going to do that first. And so let's just kind of think what kind of things have to be there in the new effective action given things that were there in the old one. For example, let's say in the old effective action, let's say at lambda, we had this quartic coupling. Okay? Now, in this full theory with the cutoff lambda, there is some process where 3 momenta come in, 3 guys go out, and it just so happens that these 3 momenta add up so that this thing in between is in between lambda minus delta lambda and lambda. That can happen. So let's say that happens. That means that this part of the answer is missing in the new theory down at lambda minus delta lambda. So I have to include it. Right? I have to include, this is something that I've integrated out, and I have to include this effect in the new effective theory. So let me put as a sort of this line to emphasize that this was in between that lambda minus delta lambda and lambda. Okay? Now let's do another example, just along the same lines. What if I have something like this, and maybe something like that? Do I need to include that? I do not need to include that, because in order for this to happen, 2 things have to be between lambda minus delta lambda and lambda, right? So this is going to be proportional to delta lambda. But this is going to be proportional to delta lambda squared, because I have to have 2 things in between. Okay? So this is the key point. This is why we get to write this exact equation and why it's so trivial to get. Okay? To get this exact equation, all we have to do is take the old effective action and draw any Feynman diagram that we can, but only with a single line in between lambda minus delta lambda and lambda. That is the effect of the fact that we've decided to compute a differential equation. Is that clear? All right, so this is one effect that we have to include. So if I'm just a little schematic here, what I would say is that there has to be a change in what I meant by H6, which is this sort of 6-point coupling, that has to go like H4 squared. And now, in the propagator, there's going to be an over cutoff squared. But there's something which is of order delta lambda over lambda, right? This is the thing which is telling me that that I'm paying the price that there's a thin shell that I'm integrating out. All right, is that clear? All right. Now, there's one other kind of effect that I could have. So let's imagine that upstairs at lambda we actually had something like this. Yeah.
You need to have some pretty special kinematics, right?
Yes, that's right. So we can come back to this. We can come back to this kind of point later. So this is where the sort of details about the fact this is not really H6. It's something which depends on momenta and so on comes in. But I'm sweeping that under the rug and only taking care of the dimensional analysis part because that's all that's going to matter for this. But you're right. This is not literally a phi to the 6 coupling at 0 momentum. We have to have the momenta add up to be somewhere between lambda minus delta lambda and lambda, right? That's why there's this delta lambda over lambda in front of this term. Okay. What about this one? Well, here I can also compute this loop diagram where only, again, the single propagator is between lambda minus delta lambda and lambda. All right? And that's it. No other loop diagram can do it. For example, let's say I have just a phi-4 interaction. See, this might be the thing you're tempted to say is the guy that you should be excited about, right? We know that that's the diagram that gives us the Wilsonian, that gives us the RG in the normal way of thinking about things. You might think this is the exciting diagram, but this diagram is not there in this exact RG. Why? Because 2 guys have to be between lambda minus delta lambda and lambda. Okay, so this guy is not there in this exact RG. Okay? But that guy is. And so what does this give us? This gives us delta H4 is, well, there's an H6, and then I have this quadratically divergent loop integral, which again, just by dimensional analysis, is going to give me a lambda delta lambda. Oops. Okay? Now, this actually exhausts everything that can happen. These are the only two things that can happen. You can just have more and more complicated blobs on this side and that side, right? But the whole point is that all we're doing is exchanging a single line. So I have complicated interaction here, complicated interaction there with this tree-level exchange in the middle, or some bigger blob with two extra legs, and I tie up the two legs together. Okay, so that's the structure of this renormalization group equation, of this exact Wilson-Pulchinsky equation. And so, being a little schematic, we write lambda d lambda of s has one piece that looks like the functional derivative of s with respect to phi squared, has another piece that looks like d squared s by d phi squared. But graphically, whoops, okay. Well, yeah, let me do this. It's useful to think about this equation graphically, and this graphical equation is everywhere in physics. Sometimes I have a slogan that most of physics is about different ways of realizing, different systems that realize this equation. Okay, so this is a very important kind of structure in both theoretical physics and mathematics. The equation, so the equation is telling us something of this form, that if you want the change of some particular piece of the effective action, it's made out of two parts. One part that looks like this, and another part that looks like that. I hope I have this right number of legs. 1, 2, 3, 4, 5. Oh, what am I doing? Anyway. 1, 2, 3, 4, 5, 6, 7. Why did I do that? I don't want 7 legs here. Okay? So this is the Wilson-Pulchinsky equation. And you can look you can look in Pulchinsky's paper for the more detailed version of this with lots of indices. It also answers Max's question and everything else. All right. But now what we want to do is solve this equation. And of course, we can't solve this equation. Notice that it's really inducing an infinite number of couplings, right? There's literally an infinite number of couplings. But to illustrate all the important points, we're going to pretend that we've truncated this equation to just two couplings. Okay, that's what Joe did in his TASI lectures. To just the two couplings that are H4 and H6. This is just supposed to illustrate the presence of a dimensionless, a marginal coupling, and an irrelevant coupling. So let's see what this equation looks like. But you know, you'll see it really has all the important physics in it. So what does the equation for H4 look like? Lambda d lambda of H4 is some beta 4 of H4 just by dimensional analysis. Depends on the cutoff squared H6. Okay, so for example, what was this equation? We just discovered at leading order this equation. This came from this diagram, from that thing. So this is equal to some cutoff squared H6 plus dot dot dot. Just that one loop, right? I mean, just from that diagram. Meanwhile, lambda d lambda of H6 is some beta 6 of 1 over cutoff squared just by units, because H6 is units of 1 over a mass squared. It's 1 over lambda squared beta 6 of H4 and the dimensionless combination cutoff squared H6. And what is this equal to? Well, this we also just saw. This is coming from this diagram. Okay? So this is just equal to H4 squared plus dot dot dot. Okay? Is that clear?
Over lambda squared?
oh, I'm sorry, yes. Thank you. Beta 4 is dimensionless. All right, good. Now let's switch to dimensionless variables. So let's switch to, as we've done before, lambda 4 is h4, lambda 6 is cutoff squared h6. And in terms of these variables, what are the equations? They're lambda d lambda of lambda 4 is some dimensionless beta 4 of lambda 4 and lambda 6. And here's the only crucial point, is lambda d lambda of lambda 6 is plus 2 lambda 6 plus beta 6 of lambda 4 and lambda 6. And that plus 2 is just the engineering dimension of h, right? So that's just the engineering dimension. All right, and that's all we need. We don't need anything else. This entire story is about the fact that this thing is perturbative, but this plus 2 is not. Okay, so it's everything's going to be about that plus 2. Okay, so the idea is to imagine, we won't solve the equations exactly, but let's imagine that we had one solution to these equations. So first, by the way, let's just see gradually what this, just sketch what the solution to these equations look like. And I'm going to draw them all in this way. So our toy model is just lambda 4 and lambda 6, but more generally it's going to be the lambda relevance here and lambda irrelevance. Okay, so let's see what these things look like. For example, we see immediately we can't just put all the irrelevance to 0 because just under scaling they're going to be generated, right? Just solving those equations immediately, you generate them. That's just what we also said a number of times in the previous lectures. So there's some curve. But here's the crucial point, is that all of these solutions converge to each other. Okay? So let's see why that is. Let's take a particular solution, lambda 4 bar, lambda 6 bar, and let's perturb around it. So I'm going to write lambda 4 is lambda 4 bar plus delta lambda 4. Lambda 6 bar plus delta lambda 6. And let's write down the equations for the delta lambdas, and there's just nothing to do. Because, again, all that matters, so I'm now linearizing those equations. So I have lambda d lambda of delta 4 is now some derivative of beta 4. So I'm not even going to bother writing down because it's something perturbative. Okay, so this is something perturbative, and this is something times lambda 4 plus something times delta lambda 6. The point is that whatever these things are perturbative. And similarly, lambda d lambda of delta lambda 6 is 2 delta lambda 6. That's the exciting part. Plus perturbative things delta lambda 4, perturbative things delta lambda 6. So all of these suckers are perturbative. What matters again is this 2. Because that 2 says that delta lambda 6, as I scale to low energies, is getting crushed down so as I go from capital lambda down to some lower scale mu, delta lambda 6 is getting crushed down to being of order mu squared over lambda squared. Okay? So this is the whole key point. You see, it's not that we can set the irrelevant couplings to 0. That is false. However, as we scale down, all of these flows are going to give me the same value for the irrelevant couplings at a lower energy mu. So if I stop at some low energy mu, the different values that I get for lambda I are all going to be the same. All the lambda I are the same up to something of order mu squared over cutoff squared. Maybe I should call this cutoff prime, just to make it clear. We're just lowering the cutoff, right? But up to over cutoff prime squared over cutoff squared. All right, and so what that means is that so long as you just give me the value of the lambda relevance down at the lower scale lambda prime, then the lambda irrelevants are just specified up to an accuracy of order lambda prime squared, cutoff prime squared over cutoff squared. And in particular, that means we can do the following thing. So it's that crushing of the flows for the irrelevant couplings that lets us prove statement 1. So, I erased statement 1, but anyway. And it's simply the following argument. So let's say I start with some garden variety value. See, I start here at lambda, but I start with some garden variety value of the relevant and the irrelevant couplings. Let me flow down. Okay? So now I have some different value for all these guys. But because everything here is, there's a nearby flow to this one. Somewhere over here, it's not the same, but a nearby flow to this one, that will go here and intersect lambda I equals 0. Right? So that's how we learn that despite the fact that I started off with things and they're definitely non-zero down there, I can just choose a slightly different theory whose predictions will only be a tiny different by power suppressed amounts, for which I can set everyone else to 0. Okay, so that's statement 1. So I have to hop from here to there and set lambda I to 0. So that's how we've proved statement 1, that g of p lambda r and lambda I is equal to g of p lambda r prime lambda I equals 0. Okay. Now what about statement 2? So again, you see that this exact RG does not give us the RG that we care about for phi to the 4th theory. It does not give us cutoff dd cutoff lambda equals 3 lambda squared over 16 pi squared. What is it doing instead? It's telling cutoff dd cutoff of lambda 4 is lambda 6. And cutoff dd cutoff of lambda 6 comes back and gives me lambda 4. Okay? So again, this exact RG is moving up along this direction. But the RG that we care about is the following one. And this is why it takes work. And this is why you still have to do calculations in perturbation theory to get it. So the RG that we care about is this sawtooth picture. Okay, so you see, it's practical because we don't need them. It's just practical to just set the irrelevant guys to 0 and work with that set of theories, right? But now I want to see how can I change these lambdas with the cutoff to keep the physics fixed. That's what I'm trying to figure out, right? So let's say I do it. I'm very happy. I begin with this theory where I've set the lambda I to 0. So here is, again, lambda r and lambda I. And I want to see how can I change this with the cutoff to keep the physics fixed. So the first thing I do is use the exact Wilsonian RG. So, okay, I'm flowing down a little bit. Oops. Now I've generated some of the lambda i's, some of the irrelevant guys, right? So what should I do? I flow a little bit. I say, oops, I generated the irrelevant one. So now what do? I know that I can fully reabsorb the effect of these guys into redefining what I meant by the relevant ones. So I do that. I go back here. Then I keep flowing a little bit. Oops, I go back here. So it's this sawtooth picture which tells me what the Wilsonian RG is here. And you see that now fits. Also, just pictorially, it fits with how we imagine doing the calculation, right? Because what is this telling us? It's telling us at the first step, I generate this guy. At the next step, having generated that guy, I'm supposed to close two of these things up. Well, if I combine those two steps together, in the first step, I generate this guy, and then in order to absorb away the effect of this one, I have to close the loop. So in total, I did this, and then I did that. Okay? And that's how I got the usual one-loop diagram that we draw. Okay? But you see, this usual one-loop diagram is not the exact RG. It is this more practical thing where you induce irrelevant operators and then absorb them away. Induce, absorb away. Induce, absorb away. And that process is what gives us the useful Wilsonian renormalization group equation. Okay? Yes?
So in this sawtooth, is it when I go up, I'm running down from lambda to a slightly lower lambda.
That's right.
As I go back down.
That's right, yeah.
It's a fixed lambda.
Yeah, that's right. It's always fixed. Exactly. That's right. So that was really the point of this. I mean, these are very closely related statements, but the first statement is with a fixed cutoff, right? Say with a fixed cutoff with this one model, there's two different sets of parameters that give me the same physics, almost, up to power corrections. And the second one tells you, indeed. So I use the Wilsonian RG to run from here to here. I lowered the cutoff. With that fixed cutoff, I absorb away the irrelevant couplings to come here. Now I keep going. Is that clear? That was an important point, but is that clear? Yes?
Sorry, why are the relevant couplings going down as you keep?
Oh, I mean, it depends on the theory. And in the 5 to the 4 theory, they happen to be going down. In QCD, they would go up. I'm just. Sorry? Yeah, sorry. Relevant here includes, I mean, all the exciting things are in the logs. Okay, so it's, yes. So, yeah, but I think, I'm sorry, I said that last time. This little r is meant to refer to colloquially relevant, which is marginal and relevant. Okay, so one more question about this sawtooth. Everything is fine? All right, so anyway, so that proves statement 2 then. Okay, so that was statement 2. So the sawtooth is a statement that we can choose lambda r with lambda and lambda I equals 0 such that with some Wilsonian RG everything is okay. Oh, by the way, the fact that there's no explicit cutoff dependence here, which is what I was making a big deal about before, is simply the fact that everything is governed by dimensional analysis here. So apart from things that occurred actually in the coupling constants, by the time we got to these equations, everything was gone. The only things that occur are the couplings. There's no explicit lambdas in the structure of the exact Wilsonian RG. So the sense in which the exact equation mattered is simply that. Such an equation exists and is manifestly cutoff independent. In other words, all that depends on the cutoff is implicitly through the couplings and not on the absolute scale of the cutoff itself. Okay? That fact, essentially plus dimensional analysis, lets everything else follow. Okay, so that's it. That's all I wanted to say about Wilsonian effective field. We set some of the qualitative consequences last time with the reason why the logs are sensibly calculable things in Euclidean space is that they get equal contributions from all scales. I alluded to the fact that in Lorenzian signature, and we'll talk about a lot more now, those same logs are associated with discontinuities and imaginary parts that have to be calculable because those imaginary parts are giving us the cross sections for particle production that's accessible at low energies. So there's both good Euclidean and Lorentzian reasons why the logs are calculable, and even in a non-renormalizable theory like the Chiral-Lagrangian, like that toy d5 to the 4 model, like quantum gravity, the logs are accessible, computable, and are universal low energy predictions that you can trust even from non-renormalizable theories. And we saw that, in fact, more generally, anything that's non-analytic in momenta, couplings, whatever, are the things that are reliably computed in long-distance effective theories. The things that are analytic are contact terms and are genuinely features of very high energy physics. And you see this very vividly in position space because the things that are contact terms are literally localized, delta function localized to coincident points, whereas the other things have power laws and are detectable at long distances. Okay, but those are some of the general remarks that we made last time already. Okay, we could at this point, yes?
So why is this useless?
Sorry?
Why is this useless?
Because, well, I mean, it's conceptually very useful. I mean, we just used it. It's, I meant, what I meant by useless is that it doesn't let you compute the beta function. You know, if you want to compute the beta function, you still have to go compute it. And this way of organizing the calculations is not particularly better than any other way of organizing the actual computation for the beta function. It's conceptually incredibly important. I just meant that you shouldn't get excited that there's some exact result that you can go and then you don't have to do any calculations anymore because it's been computed exactly already. Okay? The thing which is exact is not particularly useful. I mean, this happens. There are conceptually very important things that are practically not particularly useful. No one has computed a beta function that's never been computed before using the Wilsonian RG. Sorry, using this exact RG. I mean, All right. There are many other things that we could talk about, but these things are more standard material you can find in some of the old TASI lectures. There's the ideas of, we've talked in a sense in one effective field theory, right? We see that if there are any heavy particles, how their effects are encoded in higher dimension operators, how we can remove them, et cetera, et cetera. Now you can start having some fun. What if you have a quantum field theory with many mass scales? So you have some very heavy particles, and let's say someone gives you, you could go either way. Let's say someone happens to have given you the theory at very high energies, but you want to make a prediction at very low energies compared to the mass of some of the particles. Well, how should you do it? If you do it in one shot in the whole theory, then you'll find, okay, you got rid of the ultraviolet divergences, that's fine, that's great. But you'll find large logarithms between the masses of the heavy particles and the low energy scales that you have, right? So those large logs are, again, the obvious hint that what you should do in the effective theory at scales way above the mass of the particle, you have the full theory that includes the particle. But at very low energies compared to the mass of the particle, you should switch to a different effective theory. Even though the full theory has the massive particle in it, it's useful to describe it with a different theory that doesn't have the particle. This different theory is wrong at high energies, but it'll be right at low energies. Okay? And in this new theory, you're not going to be punished with these big logs with this big massive particle because it's not there, right? So it's a different theory. So this is the only slightly conceptually interesting point. And colloquially, we say that we just integrate things out and we match to a new theory, and it's all perfectly correct. But if you want to be slightly anal retentive about it, which I don't want to do, but anyway, just to say it just conceptually precisely, let's say you have a situation where you have say you have a situation where you have a massive particle m. Let's say I had a theory, phi, well, I have a phi and a chi, and chi has a big mass, m squared, chi squared, and so and phi is massless. So upstairs I would have loops that involve just phi, but also loops that involve chi. Downstairs I only have phi. Well, this is the colloquial way we would talk about it as effective field theorists. Well, what this really means is that there are two different theories. One of them, they both have some UV cutoff. Who cares what it is? They both have some lambda. One of them also has this particle in it. The other one does not. Okay? These are two different theories. In this theory, if you sat there and computed responsibly in this theory, you would find all sorts of things that go like log m over p. Okay? And those things can become large. And to include those in the renormalization group equations of this big theory is a bit of a pain in the ass, because you have to now figure out how to include the massive and mass-dependent renormalization group, blah, 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 blah. Okay? But there's no reason to do that. Instead, you say at very low energies, I don't even know this guy's there, so there's a new effective theory. This theory has some coupling constants, maybe some lambda for the phi to the 4, some kappa for this new interaction. This has its new coupling constants, lambda tilde just for the phi to the 4 of this theory. So they have different coupling constants. And so what you have to do, the words is you have to do running and matching. Okay? But conceptually what you're trying to do is just make sure both of these theories, you choose the coupling constants for both these theories to reproduce the same low energy physics. How should you do that? To do that, you want to find a convenient place at which to compare these two theories. And the convenient place to compare the two of them is right around the scale m. Why is it convenient? Because certainly above m it's stupid because this theory doesn't even see that particle is there. And way below m it's bad because there are big logs here. But if you do it somewhere in the neighborhood of m, then if you compute something in this theory and compute the same thing in this theory, then that tells you what to call the coupling constant of this theory in order to then be able to do physics with this theory. Now in practice, when you're working at one loop, this is extremely simple. It means you use the renormalization group equations of this big theory to run the couplings from wherever they started down to the scale m. At the scale m, you just say, kappa, you're gone, goodbye, I don't know about you anymore. And now I have just lambda left, and the lambda of this theory at the scale m is exactly what I got from the full theory running down to the scale m. So this is called running at one loop and matching at tree level. All right? Now, let's say you said, can it be m? What if it's m over 2? You can do m over 2. You can put anywhere around here that you like, and you'll get the same answer. All right? But let's say you want to do this more accurately. So what this level of matching is going to do is guarantee that all the leading logs in m over p are correctly reproduced. Let's say you want to keep going and match all the subleading logs in m over p. Then what do you need to do? You need to run it 2 loops and match it 1 loop. Is that clear? Right? Because now you're trying to get the subleading log. So somewhere in this neighborhood, you do a full 1 loop computation in the full theory and in the effective theory. And then you match the coupling constants now to 1 loop accuracy. And then after you do that, you're fine and merry. You can use the RG at 2 loop level to run down to lower energies. And now you'll have things that are accurate to subleading logs in log m over p, and so on. Okay? So what are the situations? And you can go backwards as well. So let's say you happen to know, someone happens to give you the coupling constants at very low energies, and you want to predict what's going on at super high energies. And maybe as you go along, you say, oh my gosh, there's a new particle now, right? Well, what do? You take the values that you measured at low energies. Again, if you want to do the most basic, simple thing, running at tree level, matching at 1 loop, you would take the low energy value, you'd run it up to the scale m. At that scale, you see that these new particles, you include them, and you run with the new RGs up to the higher scale. You should do 1 or 2 examples like this for fun. It's just very, very simple. Any of you who've done supersymmetric theories, you do this all the time when you integrate things out, blah, blah, blah. It's very simple. But tree level matching 1 loop running is very simple. If you ever have, if you want to have fun for a few afternoons, it's worth one time in your life doing a calculation where you do a 1 loop matching just to see how it works. Okay. Now, what are some examples where of the 2 types? Well, the most familiar example is we measure things at low energies. We might want to extrapolate to know what they are at high energies, like an asymptotic freedom in QCD, right? So that's the typical way. Sometimes, though, we have a theory that tells us something about what's going on in the ultraviolet. Let me give you 2 quick examples, classic quick examples. One of them is grand unification. Okay? So let's say the real gauge group of the world is SU5, and at some scale, the gut scale, it's broken down to the standard model, SU3 cross SU2 cross U1. In this case, the full theory is an SU5 theory with a Higgs mechanism that breaks SU5 down to SU3 cross SU2 cross U1. And there are these massive gauge bosons that are which are not in 3-2-1, the X and Y gauge bosons of the SU5. And if you did computations in this full SU5 theory, you would find large logs, log of m of the X and Y gauge bosons divided by the low energy scale. Okay, so what I want to do is instead use a low energy effective theory that's just the standard model. Okay? And now, where should I compare them? I should compare, some physical process, some simple calculation at around the scale m gut. But the thing to compare is essentially the gluon-gluon interactions and the W and Z interactions and the hypercharge interactions, or more directly, what we would call G3, G2, G1, the 3 gauge couplings of the standard model, because in the SU5 theory at tree level, they're all equal to each other. Okay, so that's a case where we have a high energy boundary condition. The fact that there's a grand unified theory tells us that if we want to do tree level matching and 1 loop running, at tree level G3 equals G2 equals G1 with some particular normalization for the G1. And then I use the standard model RGEs to run to low energies. That's how we get this beautiful picture of the unification of couplings from the bottom up. Okay, we can take the couplings that we've measured, we can run them to high scales and see that they actually come together. Especially if we include supersymmetric particles. They come very close to a meeting at the sort of % level accuracy. But from the top down, it's because there's a reason why we're given that boundary condition, the assumption of unification. It's interesting that I can make that calculation without knowing anything about the details of how the gut was broken, what are the Higgses, what are exactly the masses of the X and Y. All of those things would occur at subleading logs, but not at the leading level. Okay? So let's say I cared to 2 loop level. Okay, so by the way, why in this particular case do I need the RG? We said it the other day. Alpha, near the gut scale, the strength of the standard model couplings near the gut scale is about a 25th. Okay? That's in the supersymmetric theories anyway. It's like a 40th or so in the standard model. And the log is 30. Okay, so alpha log is just 1. So you have to do the RG just to get things accurate to order 1. If you want to get things accurate to a % level, now you have to work at two-loop subleading logs. Alpha squared log is now of order of percent, right? And so if you want to include effects whose size is of order alpha squared log, you have to do two-loop running and one-loop matching. And now one-loop matching knows all about the details of how the gut was broken, where are the X and Y's, who are the Higgses, all of the rest of that now actually needs a real model for what's going on at the gut scale. So it's kind of cool. We're a little bit lucky that alpha is small at the gut scale, that we can get this clue for unification at 0th order without knowing anything about the details of how the gut is broken. But the detailed corrections really do depend on that. Another example is string theory. Okay, like perturbative string theory in many, many of its avatars, all of its avatars, has some universal dilaton that sits there as an overall coupling constant for all of the gauge fields. So string theory gives you a reason independent of grand unification why you might have this high scale boundary condition. Now at string tree level, so at tolerance in alpha prime, but at string tree level, that all the couplings are equal to each other. And therefore, once again, we don't have to do a one-loop calculation in string theory, despite the fact that naively we're doing a one-loop correction, but it's all dominated from low-energy physics. So we can talk about running down to low energies, even if the full theory is string theory. And we use exactly the same one-loop renormalization group equations. But once again, if you want to know what the subleading corrections are very precisely, now it really matters. You have to do a calculation of the actual string theory, and these one-loop, sometimes they're called threshold corrections, but this is just doing the one-loop matching calculation. Now really has to be done in whatever string background you've chosen. The answer depends on the background. Okay, so anyway, there's many things like this that we could talk about, but these things are covered in more traditional treatments of effective field theory, although I'm happy to talk about it later as well. So here now, let me stop and ask if there are any questions about this, because we're now going to switch to the Lorenzian world. Everything crystal clear? Just out of curiosity, how many of you have essentially seen this argument before? Because I don't actually have a very, very good idea. Okay, not quite as many as I would have hoped, but anyway. All right, great. Okay, so let's now switch gears, and I want to talk about Lorentzian aspects of effective field theory and Lorentzian constraints on effective field theory. And here we said it qualitatively already on the very first day, but we just finished saying that in this sort of Wilsonian picture of the world, if you're stuck at low energies, you can't really say anything about very high energy physics, right? All the effects of high energy physics are suppressed by these scales, p squared over lambda squared. And the only time you can maybe see something about high energy physics is if it happens to violate a rule of the low energy theory. Right? If it has accidental symmetry, some process that's zero in the low energy effective theory that's dominated by what comes from high energy physics. Well, that's exactly what actually happens in Lorentzian signature. And I want to stress this point. I said it qualitatively already once, but let me say it again. This entire beautiful Wilsonian picture that's so hardwired into our thinking about quantum field theory is completely Euclidean. Totally 100% Euclidean. The separation of the whole idea of separation of scales, small distances, long distances, a completely 100% Euclidean idea, because it's just not true in Minkowski space, right? In Minkowski space, if I want to talk about small distances, I would say 2 points, x and y. I have to say x minus y squared is very small. But x minus y squared very small does not mean you need a microscope to see it. They can be super duper far apart from each other, but very close to the light cone. Okay, so that already is some clue that what we think of as effects that are coming from very, very tiny distances in Euclidean space might become visible macroscopically if we look really close to the light cone without a microscope, right? And what we want and so we're going to sort of leverage that and find that there is extra consistency conditions on effective field theories that come from Lorentzian theories that are not there in generic, garden variety other systems that can give us long distance effective theories. Okay? So everything we're now talking about, it's crucially about Lorentz invariance and causality. All right? These do not apply to underlying condensed matter systems, for example. Right? And it's this business about locality is very deep. We like to say, as in Max's lectures, for example, that you have these simple lattice models and so on, and they look local. We even say the word local. They're not actually exactly local. None of these lattice models are exactly local. If you take one of these models and ping things over here a little bit, instantaneously, arbitrarily far away, there's a response. It's exponentially small, okay? But it's not zero. This fact that there's a light cone in the real world because of this deep symmetry of Lorentz invariance is it's not an accidental, irrelevant thing. The sharpness of it is quite remarkable. And it does not occur even in systems that appear on the face of it to be local. So I just invite you to do this little exercise. It's kind of trivial to see that it has to be true. Imagine we have our balls and springs system, and I just want to see what is the 2-point function. I ping something over here. I claim instantaneously, arbitrarily far away, there is a response. Why does it have to be the case? Because anything I do is analytic in all the parameters. So make the number of parameters 2. And then there's clearly a response. Okay? And then you can see it more explicitly. Of course, you know that there's phase velocities, blah, blah, blah. The dominant thing is localized on whatever the velocities and the dispersion relation. That's all true. But there's an exponentially small tail that goes out arbitrarily far away. Okay? It's exactly the absence of those things in an honest Lorentzian variant theory that's going to give us new constraints that are not there in generic systems. And that's what we're going to be talking about. Okay, so let's actually jump to, just so you immediately get a flavor for what's going on, let's jump to a specific example. So here's my first toy model. We'll talk about again and again. So let's call it pi. I usually call it phi, but anyway. So let's say we have an effective Lagrangian for some scalar field, and there's some coupling constant divided by some mass scale to the 4th, d pi to the 4th, plus ... Okay? So this is some higher dimension operator, and in fact, as we talked about already, it's the leading higher dimension operator you would have if you insisted that the theory have a shift symmetry under pi goes to pi plus constant. Okay? Now, in the Wilsonian picture, this is some random higher dimension operator. We don't know what it is, and it comes from high energy physics somehow. Okay? But in fact, in any Lorentz invariant, unitary, causal, underlying physics, we always have to have that this coefficient is positive. And let's talk about why that is. So, well, first, before talking about why it is, let me actually just show you a bunch of examples. So some examples. Well, this thing, pi, looks like the Goldstone boson for a broken U1 symmetry, right? Just has a shift symmetry, just one field. So let's say that the underlying theory was just an abelian Goldstone model. So I have a charged scalar field phi, okay? And so usual Lagrangian d phi squared minus some potential. Okay? And so so if I expand around the Bev as usual, V plus the heavy mode, the Higgs, e to the I, pi over V. Pi is the Goldstone. So this is like the Higgs, and this is like the Goldstone. Then the Lagrangian looks like 1 plus H over V squared, B pi squared. And then there's stuff for the Higgs. So there's a dH squared minus some m Higgs squared, H squared. This is lambda V squared, and so on. Okay? But we can see already that there's this coupling H over V d pi squared. And so when I integrate out the Higgs just at tree level in this theory, I'm clearly going to get a fixed sign for this coupling, right? I'm just integrating something out at tree level, so I'm just going to get that coupling squared, the thing sitting in front of h over v squared, and I get a fixed sign. Okay, so I get pi, and a Higgs, pi, and this, in fact, indeed gives me 1 over v squared m Higgs squared d pi to the 4th, which you can think of as lambda over m Higgs to the 4th d pi to the 4, and this is indeed positive. All right, let's do another example. Let's stick with this example and say that on top, let me just erase. So let's say that in addition to these guys, we had a Weyl fermion that got a mass by coupling to phi. Okay, so let's say I had some coupling y, phi, some psi conjugate psi. Okay? Now you know that after phi gets an expectation value, psi picks up a mass, and I have a derivative coupling of the Goldstone boson to the axial current. So now the Lagrangian is going to contain something that looks like psi bar, sigma bar mu d mu psi. This is just the axial current, psi conjugate plus sigma bar mu psi conjugate times d mu pi. And now from the fermions, I get a one-loop contribution. Okay, so there's a diagram that looks like this. Right? And now this one you can't guess the answer for without doing the one-loop computation, but let me just tell you that this ends up being 1 over 48 pi squared v to the 4th d pi to the 4th. Once again, the coefficient is positive. So in this first case, we somehow saw it's positive because it's the square of something. Okay, well, here it's a little bit less obviously the square of something. There's already an invitation to think that this positivity has something to do with unitarity. Right? So it has something to do with the fact that in these diagrams, we have the same thing on one side and the other. So even here, it's like the same thing on one side and the other, even though we can't do the computation in our head. Let me do a completely different looking example. So if you look at a brain fluctuating, moving in higher dimensions, then the position of the brain in the higher dimensions, let's say in just a fifth dimension, is given by a scalar field you could call y, which only depends on coordinates along the brain x. If you haven't seen this before, don't worry about it. But anyway, there is a famous effective action that's just the analog of the effective action for the point particle, the integral of m d tau, right? The Nambu-Goto action, the analog of the Nambu-Goto action in general. Well, the analog of that effective action in general is the Born-Infeld action, which only for the scalar field takes the form of the square root of 1 minus. So the whole Lagrangian has a minus the tension of this brain. Sometimes it's called some scale f to the 4th. But this is really the brain tension. So this is a 3 brain square root of 1 minus dy squared. Okay, and if you expand this guy out, indeed, you get a dy squared plus dy to the 4th with a plus sign with a plus coefficient and so on. Okay? In every example you know, you can go check, look. If you expand out, you find that the coefficient of this higher dimension operator is positive. So why is it positive? And this positivity, it has an infrared avatar and an ultraviolet avatar. Yeah. Oh, sorry. The question is, does this depend on the fact that I integrated a fermion? Could I get a different answer if it's a different kind of particle or whatever? The answer is, for the reason you'll see, it does not matter. Okay? So, okay. So, but let's get a sense for what's evil about the wrong sign. And what's evil about the wrong sign is simply the following. We're used to this idea that Lorentz invariance guarantees that nothing can go faster than the speed of light. And this is just wrong. Lorentz invariance says nothing whatsoever about whether the things can go faster than the speed of light or not. Lorentz invariance, as a symmetry, simply says that if you have a solution to the equations of motion, whatever they are, if you do a Lorentz boost on them, you get another solution to the equations of motion. Okay? But in and of itself, it doesn't tell you anything about whether those solutions are good and bad. Okay? It's the fact about two derivative theories that we know and love for which Lorentz invariance implies that nothing can go faster than light. But now we're talking about effective theories with higher dimension operators. Okay? Now, normally, and this is part of the ideology that we just talked about, normally we say, well, the effect of higher dimension operators is tiny, and it's only important as you get close to the cutoff. But when you get close to the cutoff, you've got to change description to a new theory anyway. So you can never reliably talk about what effects you get from higher dimension operators. They're either big effects, they're either tiny, or you've got to get up to the scale, and then you've got to change the description of the physics. But see, that's exactly not true, because in this case, we're precisely in one of these situations where the standard low-energy two-derivative physics predicts 0 for some quantity, puts you right at the edge of something dangerous, which you then have to check whether the corrections push you in the right direction or the wrong direction. And what is it that's critical here? What's critical is that in the standard two-derivative theory, the excitations of pi travel exactly on the light cone. Okay? So there's things, pi excitations travel exactly at the speed of light. But now we can imagine turning on some non-trivial background for pi. Okay? So let's turn on a background for a pi. So I'm going to turn on a background for pi where pi dot is a constant c. Right? And I'm going to imagine that c squared is arbitrarily tiny. C squared is arbitrarily small compared to m to the fourth. So this is a background. Let's call it pi naught. So I've made it arbitrarily tiny, which means that I can't say that all the higher terms are going to come in and swamp what I'm talking about or being comparable. No, all the higher order terms are tiny compared to anything I'm getting from this, because I'm ensuring that c squared is much smaller than the cutoff. Now, this is a translationally invariant background. By the way, you can trivially check that it's a solution to the equations of motion. Okay? In fact, pi is a translational symmetry, so it's clearly a solution of the equations of motion. But now what we can do is look at small fluctuations around pi. So pi, let's put pi as pi naught plus delta pi, and look at the effective Lagrangian for delta pi. And you can just work it out. But you see, I mean, you don't have to do any algebra. The background breaks Lorentz invariance. Right? Nothing wrong with that. You and I break Lorentz invariance. Everything in the world breaks Lorentz invariance. Okay? But importantly, this is a translationally invariant background. So I still have spatial translational invariance. And therefore, there's a well-defined notion of speed of propagation. I still have waves. I still have translational invariance. I still have wave solutions. There's a well-defined notion of speed of propagation. All right? So there's a well-defined dispersion relation. So let's see what the dispersion relation in this background. But again, we don't have to do any work because it's clear the dispersion relation won't give me a speed that's 1. And now, depending on c, I'm going to get one sign or the other. So it's not guaranteed that I'm going to go slower than light. Just to be complete about it, the Lagrangian that you get, you just work out the effective dispersion relation. So just from the pi dot squared parts, when you take the d pi to the 4 term and expand around pi dot and keep the quadratic pieces, then I have something that looks like a to mu nu plus 4k over m to the 4th. Oh, sorry. I don't know why I said c. Oh, sorry. Yeah. 4k m to the 4th c squared. C mu c nu d mu d nu phi equals 0. Pi equals 0. And here what I've said that d mu pi naught equals c mu. So literally in this case, just c0 is not equal to 0 and is given by c. Okay, sorry, so now there's no c squared there. Okay, so that's the two derivative equation of motion around this background. And so I find the dispersion relation that's omega squared is equal to k squared, but over 1 plus 4k over m to the 4th c squared. And so you see, bad notation, I'm sorry, kappa. Okay? So you see, if this coupling constant is positive, then the speed of propagation is smaller than the speed of light. But if the coupling is negative, then the speed of propagation is bigger than the speed of light. The Lorentz invariant theory, Lorentz invariant Lagrangian, but it does not guarantee that excitations travel slower than the speed of light. Now we could have a lot of fun talking about why this is bad. Why is it bad to have things going faster than the speed of light? And I would be delighted to talk about this at night or over the break, because there's all sorts of fun things to be said about it. It is bad. Okay, it is bad, but it's not for the reasons that are often said when we teach special relativity very early on. For example, the classic reason that it's very bad because when you in a different frame, when you send a signal from A to B, B receives it before it's sent at A. This is not a good reason, because what's really happening is that B receives it when the time on B's watch is earlier than the time on A's watch when they sent it. And that happens every time you're on the East Coast and you send an email to a friend on the West Coast. Okay? So that is not the problem. Okay? So there are deep problems, but that is not it. And so we could spend a lot of time talking about it. If you read the paper we wrote on this subject ages ago, a big part of this paper is just having fun, talking about what's bad about going faster than light. But let's bank that discussion, and I hope you believe me that it's bad to go faster than light. But in any case, it does mean the following: but this is maybe one of the most convincing, least technical ways of saying it. What is the point of Lorentz invariance after all? It means out that you can't reach out and touch someone, right? You can't have instantaneous action at a distance. And if you want to avoid stupid discussions with friends who want to talk about phase and group velocity and this and that, definitions and so on, you should just ask, whatever the heck you're talking about, doesn't let, if your loved one happened to be in Alpha Centauri for some reason, would the effect you're talking about allow you to pick up a phone and talk to them now? Okay? If you can pick up a phone and talk to someone in Alpha Centauri now, despite the fact that they're 4 light years away, then you've reached out and touched someone, right? Then despite the underlying Lorentz invariance and so on, you actually have action at a distance. And that's exactly what's allowed in this theory. If pi existed, if this was around, then all you'd have to do, you would just have to make a lot of pi, make a big, capacitor plate, pi capacitor plate, and just make sure that when your friend goes to Alpha Centauri, they're like, take this pi capacitor plate with them, so you stretch this capacitor plate across the galaxy, and then that's great. You pick up your pi phone and you talk to them more quickly than you could otherwise. Okay, maybe not immediately, but certainly, well, then if you boosted everything, you could talk to them arbitrarily. You could talk to them as quickly as you want, because in this case we went a little faster than light in this frame, but now I can boost this frame, and I can boost this frame and tilt the pi light cone as much as I like towards so what you really have to do is have someone constantly running with these capacitor plates really fast. Okay, so you pay them a lot of money, and if they do that, then you sit here and you pick up the pi phone and you talk to your friend instantaneously. Okay, so that's bad. And we can then talk more technically about why it's bad and so on. But in every physical sense, this is a useless Lorentz invariance. It doesn't buy us the things that Lorentz invariance we think buys for us, that it prohibits it prohibits action. It prohibits action at distance. I stress this because this is the long-distance avatar of UVIR decoupling in the Wilsonian picture, right? This is exactly, if we could have the wrong sign, then we could leverage something going on at very, very high energies to be able to win at very long distances. All right? And so we're saying precisely that should not be allowed to happen in a theory that has healthy decoupling of scales. Okay? And indeed, if the theory came from Wick continuing from Euclidean space to Minkowski space, of course, this can never happen. It can never happen in an underlying local quantum field theory. Why can't it happen in an underlying local quantum field theory, by the way? Very quick reason, very quick argument. Why can't it happen in an underlying local quantum field theory? The famous statement of locality in quantum field theory is that operators commute with each other at space-like separation. Okay? It's very important that that's an operator statement. It's not a statement about some Green's function, which might depend on the background, but it's an operator statement. Now, everything that we're talking about and commutators of fields are what gives you retarded Green's functions. Okay? So even you turn on some system, you want to see what the response is to a turning on a perturbation to the Hamiltonian. At leading order, for the 2-point function, the response is simply given by the commutator of the perturbations that you would turn on. It's the commutator that gives you the retarded Green's function. Okay? So the fact that the commutators as operator statements vanish outside the light cone means that no matter what background you sandwich this in, be it the vacuum or this lump of pi that I want to turn on, or anything, it cannot go outside the light cone. Okay? So that's why this operator statement implies the impossibility to send any signals faster than light. But we are interested in things that don't come from local quantum field theory as far as we know. We might be interested in some kind of stringy UV completion of the standard model. Okay? Are the rules totally different there? Well, it's true that we don't quite understand what the analog of these rules are in string theory. String theory is explicitly, string theory in flat space is explicitly an on-shell theory. It only talks about S-matrix elements. And we're going to transition to doing that right now and start talking about all of these things from a different perspective, from the perspective of analyticity and unitarity of scattering amplitudes. But just to say the right answer, it turns out that string theory satisfies more stringent conditions than quantum field theory, not less. Okay, so you shouldn't have this idea that when you exit quantum field theory and go into string theory, you're like in the Wild West. It's the other way around. It's even more constrained. Okay? You have the constraints you had before and better ones, more ones. So everything we're talking about is also true in string theory, and we'll understand better why it's true in string theory when we describe what's going on from the perspective of scattering amplitudes. Okay? All right. How am I doing for time, Professor?
About 5 minutes.
5 minutes. Okay. That's great. Awesome. Do you like ice cream? Is there any...
Are you trying to bribe it?
I am trying to drive it. This is how wholesome I am. I can only imagine bribing you with ice cream. All right. Okay. So let me just say a few things, and then tomorrow we'll have to have a fight with Oliver, I guess. But we can continue to be friends today, so long as I'm still here. Okay. All right. So before moving on, let me starting the discussion. Let me just say exactly the same thing happens in a lot of other examples. For example, if you have a Maxwell theory, that's the leading Lagrangian, and then we have corrections that can look like some kappa 1 over m to the 4th f mu nu. So Euler-Heisenberg type corrections squared plus kappa 2 over m to the 4th ff dual squared. Then once again, all of these coefficients are positive. And you can discover that they're positive by once again turning on a spatially translationally invariant background. So you turn on a uniform background electric field, a uniform background magnetic field, and you can look at the small fluctuations of photons of different polarizations even, and you conclude that all of these coefficients have to be positive. Okay, now we're going to. So I'm not going to do it, but let me just set up why it is that this question. So we've described this purely from the long distance perspective. There's something wrong when I turn on these backgrounds. I can go slightly faster than light. Now I want to say that all of this, and in fact much more, is guaranteed by something else, which has to do with looking at the properties of the 2-to-2 scattering amplitudes for pi-pi scattering. So now, why should these things be related to each other? Well, the most basic reason, what is it that is going on? As the most basic reason, what's going on when I turn on this big background and I'm looking at the propagation of pi through it is just this. Here's delta pi coming along, and it can interact with the background. Okay, and again it gets kicked somehow, and it interacts with the background again, and gets kicked again. It interacts with the background again, it gets kicked again, and so on. Okay? this propagation of pi, of delta pi, the fluctuation through the medium pi, is like having over and over and over again this underlying 2-to-2 scattering with the stuff that's making the blob. Okay? So this now tells you that what's going on is that in some sense, this elementary scattering process there is giving you a little tiny advancer delay. Right? That little tiny advancer delay, you might think as an effective field theorist, I don't care, that's up near the cutoff. Who knows what's going on up there? It'll be a little tiny advancer delay of order of the cutoff, 1 over m. Okay? But in the spatially invariant background, it just adds up again and again and again and again and again, and you can let it keep going and enhance this effect that you're seeing from the microscopic 2-to-2 scattering and actually see it as something that you can measure macroscopically at long distances. Okay? So this is at least some bit of intuition why the presence or absence of superluminality at very long distances is somehow related to whether this 2-to-2 scattering process somehow respects causality or not. Whatever that's supposed to mean. Okay, but there's some kind of elementary 2-to-2 scattering process, and the constraints, physical constraints on that 2-to-2 scattering process are getting concatenated to one way or another tell us whether you either are in or out. Okay, so that's why it's at least intuitive that it's reasonable to think about what's going on with this 2-to-2 scattering amplitude. And so let me just tell you what we're going to talk about. I'm not going to say anything in detail. The claims are that that causality and unitarity are going to force these couplings to be positive. Okay? Now, in order to do that, I have to tell you what causality and unitarity mean concretely about this 2-to-2 scattering amplitude. Unitarity is pretty easy, okay? And we will talk about what it means, but it's relatively familiar. Causality is harder. And that's because, and this is an unsolved problem to this day. It's incredible in the year 2019 we don't have the answer to this very basic question. But the physical question is simply the following. You're an experimentalist at CERN. You collide particles in the morning. You go to the canteen. You have your espresso. You come back at night and you see what came out of the experiment, right? So you're not in the proton. You don't follow what's going on and see, oh, this gluon hit that guy, then this happened, and that happened, and the other thing happened, and then it came out into the detector and it lit something up. You don't see any of that, right? All you see is the thing that went in and the things that went out. What you see are these asymptotic observables. As quantum gravitationalists, we love these asymptotic observables. In flat space, the analog of ADS boundary correlators in flat space is the S matrix. So this was the first boundary observable that people ever talked about. Okay? The problem is that we know much less about the S matrix, ironically, than we know about boundary correlators in ADS. We know vastly less about the S matrix. Okay? And that's just this basic difficulty that we don't know. How is the fact that the evolution on the inside of the space-time was causal somehow reflected in this answer that you just see asymptotically far away? Now, in the 1960s, now there's a cousin of this problem, which we're all used to, and people understood in the 1800s, and you study in Jackson, and we all know about, which is if you talk about two-point functions. Okay? If you talk about two-point functions, then we know what is the fingerprint of the fact that a two-point function is causal. In other words, it vanishes when t is less than 0, and it turns on when t is bigger than 0. What is the fingerprint of that in Fourier space? Okay? And the fingerprint has to do with the analyticity properties of the Fourier transform. Okay? The Fourier transform is an analytic function of energy in the upper half plane. And it has, we'll review it next time, but it has to be polynomially bounded. It has to be beaten by an exponential in the upper half plane. You see that very, very simply by writing the formula for the Fourier transform, observing the integral over time just goes from 0 to infinity, and therefore when you integrate that against e to the I energy t, you can clearly continue it to when the energy has positive imaginary part. Okay? So somehow, for two-point functions, we know the answer, and we know the answer has something to do with the analytic structure of the analytic structure of the object in the energy space. So that tells you that causality for scattering amplitudes is somehow encoded in whatever the analytic structure of the amplitudes are as a function of complex momenta in general. Okay? And that's what the S-matrix theorists of the 1960s hoped, that they would be able to somehow derive from the top down what are the analytic properties that you need derived from causality, from God somehow, on the scattering amplitudes in order for it to be compatible with causality. And they couldn't figure it out. And we still don't know the answer to this day. Okay? This is one of these deep problems that has not gone away and is not likely to go away until someone figures out how to think about it properly. And it's a basic fact about the actual real world that we don't have some simple understanding for. Okay? But we know it has roughly something to do with the analytic properties, and there's one situation where we do know enough to say something about it, where we can make progress and say the kind of statements that we're talking about. And that is when you're doing scattering very close to the forward limit. Okay, imagine you're doing scattering very close to the forward limit. So if we're imagining a scattering as a function of S and T is very small. So imagine you keep T fixed, and now you think about the amplitude as a function of S. In this limit, despite the fact that we're talking about a 2-to-2 amplitude, it's physically the same as the propagation of one particle in the sort of soft background set up by the other. So in this limit, it's very close to a 2-point function. And because we know the answer for a 2-point function, we can make claims about what the analytic structure of the scattering amplitudes are for the 4-point amplitudes close to this forward limit. Sometimes people think it's literally in the forward limit, and it's not literally in the forward limit. That's these are some things that were known. If this was a school in the 1960s, I wouldn't have to explain these things. But none of this thing is in any of the textbooks anywhere anymore. So part of what I'll do tomorrow is explain these things and tell you what we actually know about the analytic structure of the S-matrix in this case where we can say something. But anyway, so for our purposes in this limited range, we can say enough to be able to say a few things about the structure of the 2-to-2 scattering amplitudes. And we'll see it's causality, the analytic properties, and the analytic properties are really encoded in the simple statement that for fixed T, the amplitudes are bounded by a power of S at high energies. The power of S never exceeds 2. It's at most S squared. And it's only S squared when the high energy theory has gravity, in fact. If you don't have gravity, you can't even hit S squared. It has to be bounded by S. Okay? But in any case, S squared is good enough for all of our purposes. So that polynomial boundedness of the amplitude, together with unitarity, are going to allow us to derive these positivity properties. Now that already was known 15 years ago. Well, really was known 40 years ago. It was repopularized 15 years ago. But there's new things that we've been discovering recently, which again begin from exactly the same starting point. By the middle of the next lecture, I'll just give you a representation, a dispersive representation for the scattering amplitude that's useful even away from the forward limit. And we'll discover an infinite number of other constraints. Not merely that things are positive, but there are all kinds of other intuitive things that you would expect. For example, you expect that if you have some dimension 6 operator that's suppressed by the TeV scale, the dimension 8 operator shouldn't be suppressed by 1,000,000 TeV. They should also roughly be suppressed by the TeV scale. That's an intuitive expectation. That means that you should expect there's some kind of nonlinear relationship between the coefficients of higher dimension operators of different mass dimension. Okay? Also, you might expect if there's a bunch of dimension 8 operators, I shouldn't be able to make one of them 10,000 times bigger than the other one. So you should expect that there are inequalities that are satisfied between operators of the same dimension. And those are all intuitive expectations, but you might think, well, maybe you can find exceptions if you finely tune, you change things around. Maybe you can make something 1,000,000 times bigger than another and so on. But you can't. And so there are an infinite number of new positivity conditions on the coefficients of higher dimension operators that contribute to a 2-to-2 scattering. And in fact, all of these constraints take the place of demanding that all the coefficients of these higher dimension operators live in a kind of interesting geometric space. Kind of geometric space that in other contexts we've called positive geometries, and which are almost identical in structure to this notion that showed up in a number of different places in physics. Completely different, unrelated parts of physics, but extremely similar underlying mathematical structure. So that's the goal for next time. All right, thank you very much. Yes.
And calculate commutator of operators which is space-like separated.
Yes.
In the silver space.
Yes.
Will you always get 0 in this background? Unless you assume that this k is positive.
Yes.
Could you repeat the question?
Yeah, sorry. I mean, the question was, let's say you quantize the theory of the small fluctuations around this pi blob. If you computed the commutator, you would find the commutator. If the coefficient has the wrong sign, the commutator vanishes outside the light cone. Sorry, it doesn't vanish outside the light cone. Yeah.
Okay,
Yeah.
so you detect from that perspective, from the Hilbert-Smith perspective, you can argue that has to happen.
Yes, you can detect it. Well, that's what I was saying when I said that it's the commutator of the perturbations that you add that are actually tell you the causal response. Okay, so I mean, probably many of you have done this exercise. If you haven't, it's a very simple exercise. Imagine you have a Hamiltonian and you just perturb it at some time, and you want to see what the response is to that perturbation. The leading order of the response to the perturbation is given by the commutator. Okay, so the two-point function is the expectation value of the commutator. So the retarded Green's function, the causal Green's function is the commutator. Notice, by the way, that the commutator is 0 in Euclidean space. Because in Euclidean space, it doesn't matter what the ordering is, right? So again, this is another one of many indications that there's action in Lorenzian signature that you don't see in Euclidean signature. But indeed, that commutator would vanish. In this particular case, the commutator is a rather heavy-handed way of talking about what we see very simply just by looking at the small fluctuations anyway, right? As I said, if this was going on, you could pick up a pi phone and talk to your friend more quickly than you could by the speed of light, which therefore, if you boosted the whole thing, you could talk to them as quickly as you like. Okay? So there's something sick about that. It means despite the fact the equations are Lorentz invariant, they don't give you the physical consequences of the Lorentz invariance that I can't reach out and affect you arbitrarily far away. Yes?
Supermassive particles, at the derivative order, they're not traveling on the light cone.
Yes.
Are there still constraints?
Yes, there are still constraints, of course. I mean, all you need is a separation of scales, right? So if the mass is much smaller than this cutoff m, then you just have to find, you can make a blob that's very big but still small compared to the constant wavelength of the particle. And so there you would go faster than light.
All right, let's thank Nima again.